This is the next chapter, permutation groups. So in this problem, we have two permutations given to us, alpha and beta. We have to compute these things, alpha inverse, beta alpha and alpha beta. So let us start. Alpha inverse is rather easy to calculate. You just see what alpha does to every number here in the first row and reverse that. So alpha takes 1 to 2, so it will take 2 to 1. I mean alpha inverse will take 2 to 1. 1 to 2. 3 is unchanged. Excuse me. So 3 will not be changed by alpha inverse also. 4 goes to 5, 5 goes to 4. So that means alpha inverse will send also 4 to 5 and 5 to 4. And 6 is unchanged. So this is our alpha inverse. Then B. So in B we have to calculate beta alpha. Now before we calculate this, let us see what we have to do actually and what this product beta alpha means. In this book, like in many books normally, what we get is this. Say we have two functions, f and g. F maps the set A into the set B and G maps the set B into the set C. Then we form the composition G composition F, which maps A into C, and it becomes somewhat confusing in the beginning when we get compositions of functions, because the composition of f and g is G composition f. Why not f composition g? Because we have changed the order. It starts with f, that takes A to B, and then from B we go to C via G. But we have to change the order because we write the image of an element x under f, say, as f of x. We write the input to the right of the function. So that's why we have to change the order in forming the composition. That is because here also we would be writing the input to the right of x, to the right of the function. So now it makes sense to have G composition f, because now you can apply f first to x and on that result we will apply G. In some books, for example in Herstein's topics in algebra, this notation is not used. Herstein uses this notation. He writes the input to the left of the function. So for Herstein, this same composition will just be f composition G, because when we calculate f composition G at some point in the domain A, so now we can apply f first and then on that we can apply G. This is one of the reasons why Herstein uses this notation instead of this one. That you don't have to change the order. If you write functions like this, f and g, if you take their composition in which they follow this natural order, then that is the order in which they appear in the notation for composition. But that's not what we are doing in this book, and this notation is less familiar. Whenever we encounter function anywhere in mathematics, most of the times it looks like this. There are some other weird notations also. More weird. Some people, for example, in Hans Kurzweil's finite groups, I think the book name is Theory of Finite Groups or something like that. He uses this notation where the function is written as a superscript. Anyway, for us this is the case. So that is why when we are calculating beta alpha, we would calculate alpha, we would look at alpha first and then at beta. So by that what we mean, and this is also composition. No, we are simply not writing this intermediate symbol for composition, and we are just writing the composition as beta alpha for the sake of simplicity. So calculating beta alpha means, for example, you have to calculate beta alpha at say 1. So that just simply means applying this composition. So that is why we have to first apply alpha and then on that we have to apply beta. So keeping that in mind, here what we will get is this. First we apply alpha on 1, we get 2. On that 2 we apply beta. So again we get 1. So that means the image of 1 under beta alpha is 1, it is unchanged. So like that, 2 goes to 1, 1 goes to 6. So 2 goes to 6. 3 is unchanged, here beta sends 3 to 2. 4 goes to 5, 5 goes to 3. So 4 goes to 3. 5 to 4, 4 is unchanged. So we have 4 here. And 6 is unchanged, this one sends 6 to 5. So this is our beta alpha. Now that we understand how to calculate this, we can calculate alpha beta also. In calculating alpha beta, we look at beta first and then alpha. So let's first write the top row. 1 to 6, 6 is unchanged. 2 to 1, 1 to 2. So 2 is unchanged by alpha beta. 3 to 2, 2 to 1, so 3 to 1. 4 is unchanged, 4 goes to 5. 5 to 3, 3 is unchanged. 6 to 5, 5 to 4, so 6 to 4. Okay, let me now see if these things have been calculated correctly. 2, 1, 3, 5, 4, 6. Okay, 1, 6, 2, 3, 4, 5. 1, 6, 2, 3, 4, 5. Okay, then 6 to 1, 5, 3, 4. 6 to 1, 5, 3, 4. Yes. So this is our first solution. Next exercise 2. Let alpha be equal to, here even a bigger one is given, one involving 8 symbols. And the second row is 2, 3, 4, 5. 1, 7, 8, 6. this is our alpha and beta 1387 6524. Right. Alpha, beta and alpha beta as there are two parts. Part A, products of disjoint cycles. And part B, products of two cycles. Okay, so let us see the solution. We don't need much space to write cycles. That is one of the advantages of the cycle notation. Products of disjoint cycles. So let us first write alpha as such a product. So alpha takes, we start like this. You can in fact start anywhere. Okay, you can start at any point here. You can in fact start at 5. It does not matter. But let us start at 1. So 1 goes to 2, 2 goes to 3, 2 to 3, 3 to 4, 4 to 5, and 5 again comes back to 1. So this is one of the cycles, and whatever is not appearing here, these things, you can then take any one of them. Say 6, 6 to 7, 7 to 8, and 8 again goes back to 6. So this is the disjoint cycle decomposition of alpha. Note one thing, that I am using commas here to separate the symbols, and I will continue to use commas. It is because of a possible confusion that can occur if you don't use commas. For example, you are given a permutation that looks like this, where suppose you are not using comma. On this set, say, so there is 5 also which is not appearing in this permutation, which means we know that 5 is unchanged by this permutation, so we don't write 5. Okay, now okay, so fine, in this set there will be no confusion. However, if you increase the number of symbols, say it goes on till say 20, so that this is an element in S20, the symmetric group of degree 20. What do I understand from this? Is it the permutation involving these 4 symbols, 1, 2, 3 and 4, or is it the permutation involving 3 symbols, one of them is 12 and the other is 3 and the remaining one is 4? that confusion, that possibility is there. So to get rid of that, I am going to use commas. Okay, I won't remove these commas. Commas usually are not written because that saves space, horizontal space, but not at the expense of confusion. I mean, sorry, the expense of clarity. And like that, we write the cycle decomposition of beta. Since 1 is unchanged, we don't write 1 cycles. Okay, we keep them hidden. So we start things with 2. 2 is sent to 3. 3 is sent to 8. 8 is sent to 4. 4 to 7. 7 to 2 again. What have we missed? We have missed 5. 2, 3, 4, yes, 5. 5 is sent to 6 and 6 again is sent back to 5. So this is beta and alpha beta. If you want to first calculate alpha beta in this format, you can do that, but actually there is no need to do that. We can directly write the cycle decomposition for alpha beta. You have to make sure that you are looking at beta first and then alpha. You have to remember that thing. So all we need to know in order to write such a cycle decomposition is what alpha beta is doing to every number. That's all. So beta does not change 1, or I should say like this, this will be easier to understand. 1 to 1, 1 to 2, that means 1 to 2. 1 to 2. 2 to 3, 3 to 4. So that means 2 to 4. 4 to 7, 7 to 8. So 4 to 8. 8 to 4, 4 to 5. So 8 to 5. 5 to 6, 6 to 7. 5 to 7. 7 to 2, 2 to 3. So 7 to 3. Then 3 to 8, 8 to 6. 3 to 6. 6 to 5, 5 to 1. So that means 6 to 1. Do we have all the symbols? 1, 2, 3, 4, 5, 6, 7, 8. Yes. So alpha beta itself is a cycle. It's an 8 cycle. And the others are, each one of them is a product of a 5 cycle and a 3 cycle. Oh, this one is a product of a 5 cycle and a 2 cycle. So what happened? Oh, it does not change one. So that is gone. That is not appearing here, that symbol. Okay, so this is part A. And then in part B, we have to write these things as products of 2 cycles, transpositions. And that we can do using one of the ways of writing a cycle itself as a product of transpositions. For example, this is our alpha. No, we can use this and start from here. So in place of this cycle, we can write 5, 4. You go like this, 5, 4, 5, 3. 5, 2, 5, 1. Like that you write this one also. 8, the product continues, okay, 8 7 8 6. So this is alpha as a product of two cycles, and like that beta seven 4 7 8 7 3 7 2, and this itself is a two cycle, so we just simply write it. And alpha beta 6 3 6 7 6 5 6 8 6 4 6 2 and 6 1. Okay, so this is the solution to the second one. These decompositions, not these ones, but these decompositions as products of transpositions is not unique. This you already know. There are other ways of, other factorizations like this of these permutations. Write each of the following permutations again as a product of disjoint cycles. What are the permutations? 1 2 3 5 and 4 1 3. P 1 3 2 5 6. Two 3 and 4 6 5 1 2. C 1 2 1 3 2 3. One 4 2. Okay, there is a high chance of making mistakes, so let me just verify once more. 1 2 3 5 4 1 3, 1 3 2 5 6, 1 3 2 5 6 2 3, 4 6 5 1 2. Okay, then 1 2 1 3 2 3 1 4 2, right. A. This is also a product of two cycles. One of them is a 4 cycle and the other is a 3 cycle, but they are not disjoint. They have this symbol common 1. So we have to write it as a product of disjoint cycles. And in doing so, we again have to keep in mind that we have to start from the right hand side and come towards left. So first, this cycle sends 1 to 3 and then that 3 is sent by this cycle to 5. That means 1 goes to 5, 1 to 3, 3 to 5, 1 to 5. Then 5 is not touched by this, 5 is unchanged by this one, and then this sends 5 to 1, so 5 goes back to 1. So this is one cycle that will appear in this decomposition. Then let us start with 2. Whenever you finish writing a cycle, you look for a symbol that does not appear in the cycle and then start from there. And that symbol can be any of the remaining symbols. So let us start with 2. 2 is not changed by this one, and this one sends 2 to 3. So 2 to 3. Then 3 is changed by this one and 3 goes to 4. However, 4 is unchanged by this. So 3 goes to 4. Then 4 goes to 1, 1 goes to 2. That means 4 goes to 2. So 4 goes back to 2. So do we have everything? 1, 2, 3, 4, 5, these are the only symbols available. Yes. So this is the decomposition of the given permutation as the product of disjoint cycles. Now the cycles are disjoint. Note that now one of them is a transposition and 2 cycle and the other is a 3 cycle. Then B, 1, 3, this is a long one, 2, 5, 6, 1, 3, 2, 5, 6, 2, 3, and 4, 6, 5, 1, 2. We start with 1 and that goes to, first 1 goes to 2. So 1 to 2, 2 to 3, 3 to 2, that means 1 to 2. 2 to 4, 4 is unchanged. Here also 4, this one does not change 4, so 2 to 4. 4 to 6, 6 is unchanged, and 6 to 1, so 4 goes back to 1, so this cycle ends here. Then let us take 3. 3 is unchanged by this, 3 goes to 2, 2 goes to 5, so 3 goes to 5. Then here 5 goes to 1, 1 is unchanged by this, and this one sends 1 to 3, that means 5 goes to 3 back. So we have this, and then 1, 2, 3, 4, 5, we have 6 also. 6 goes to 5, 5 is unchanged, 5 goes to 6. Oh, so 6 is not changed by this entire permutation. So this is the product of disjoint cycles. One of them is a transposition again, and another one is a 3 cycle. There is always a doubt lingering in the back of my mind that after calculating such a thing I must have made a mistake. Let me just see. One, 5, 2, 3, 4. 1, 2, 4, 3, 5. Oh, and we have another one. Huh? These two are correct. 1, 2, 1, 3, 2, 3, 1, 4, 2. 1 to 4, 4 is unchanged by these 3, so 1 to 4, 4 to 2, 2 to 3, 3 to 1, and 1 again goes to 2, so that means 4 to 2. Then 2 to 1, 1 to 3, and that's it, so 2 to 3. 3 doesn't appear here, 3 to 2, 2 to 1, so 3 goes back to 1. Yes, so this is a single cycle, a 4 cycle, 1, 4, 2, 3. That is the solution. Find the order of each of the following. Okay. Following permutations. One, 4, 1, 4, 7. 1, 4, 7, 6, 2. Okay, first 1, 4, then 1, 4, 7, then 1, 4, 7, 6, 2. This is reminding me of something. That's why I am smiling. A sequence from a film. Anyway, and the last one, this one is general. A, K. So it's a 2 cycle, so its order is 2. According to the notation that is being used in this book, this denotes the order of this element. So this is 2. Then in the third one we have a 3 cycle. So its order is 3. In the second one I said third one, and in this one this is the 5 cycles, so this is 5, and here this is the k cycle, so the order is k. You can see that here all the permutations are each one of them is a cycle, so we just have to know the order of an n cycle. It is n, so that's why this. Now if you have some doubt about this being a k cycle, you may suddenly you may have this doubt that can this be written as a product of disjoint cycles in some other way? No, because this is itself a single cycle, and these symbols that appear inside a cycle, they are all distinct. Keep that in mind. So that is why you have to find the kth power of this in order to get the identity in the group, in the permutation group. Any positive exponent smaller than k will not give you the identity. For example, you can see, let us consider this one, 1, 4, 7, then it will become clear. You probably already know these things, but let's see them for once in details. If one calculates the positive integral powers of this 3 cycle, the 3 cycle itself is its first power, which is clearly not equal to the identity permutation because it changes things. It takes 1 to 4. What is this? So this will be a product of it, 2 copies of it. So first 1 goes to 4. Since both of them are the same, so you don't have to really think about the order. 1 goes to 4 and then 4 goes to 7. So 1 goes to 7. 7 to 1 and 1 to 4. So 7 to 4. Then 4 to 7, 7 to 1. So 4 to 1. And when you calculate this, then it is 147 square times 147. That means 174,147. So we have to start from this side. Actually, in this case, it does not matter because you could write this also as 147 times 147 square. Anyway, let us keep the rule intact. 1 goes to 4, 4 goes to 1, so 1 is unchanged. 4 goes to 7, 7 goes to 4, so 4 is unchanged. Like that, 7 goes to 1, then 1 goes to 7, so 7 is unchanged. Whatever other symbols that are there in the underlying set, they anyway are not changed by this, any 2 of these, so together also they won't change those remaining symbols which are not appearing here. So that means this does not change anything, and so this is the identity permutation, and that's why the order of this is 3. The same argument goes for a general k cycle or n cycle, anything. So that's just it, and I need ink before I write anything else. What is the order of each of the following permutations? One, 2, 4, 3, 5, 7. B 1, 2, 4, 3, 5, 6, 7. 1, 2, 4. 3, 5, 6, 7. C 1, 2, 4, 3, 5. D 1, 2, 4. 3, 5, 7, 8, 6, 9. E 1, 2, 3, 5. A 4 cycle. 2, 4, 5, 6, 7. Okay. There is one more. F 3, 4, 5. 2, 4, 5. So let us first recall the theory. When you write a permutation as a product of disjoint cycles, the order is the LCM of the orders of those cycles. And for each cycle we already know how to calculate the order, so it's just a simple matter, but we have to keep in mind that the cycles should be disjoint. Okay, in this last one you can see they are not disjoint, they have this common symbol 4, so we have to first express it as a product of disjoint cycles, and then we have to apply that theory. Here the cycles are disjoint, 1, 2, 4, 3, 5, 7, no symbol is common to them. So here you just simply write like this, the order is the LCM of, okay, the order of this is 3 because it's a 3 cycle, and this one is also a 3 cycle. 3 and 3, so this is equal to 3. So this itself has order 3. Then T, 1 is not there, 2 is not there, 4 is not there, so these are also disjoint cycles. And the order is the LCM of 3 and 4, which is 12. So its order is 12. C. Here also the cycles are disjoint. Three and 2, that is 6. Then D, 1 is not there, 2 is not there, 4 is not there, so these are also disjoint. This is a 3 cycle. This part is same in the first 4, and this one is 1, 2, 3, 4, 5, 6. So here the LCM is again 6. E. These two are not disjoint. 2 is common to them. So we first express it as a product of disjoint cycles. 1, 2, 3, 5. 2, 4, 5, 6, 7. One is unchanged by this, 1 goes to 2. 2 to 4, 4 is not here, so 2 to 4. 4 to 5, 5 to 1, so 4 comes back to 1. Then let us take 3. 3 is not here, and this one sends 3 to 5. 5 to 6, 6 is not here, so 5 to 6. 6 to 7, 7 is not here, so 6 to 7. 7 to 2, 2 to 3, so 7 comes back to 3. Okay, 1, 2, 3, 1, 2, 3, 5 here. Anyway, have I missed anything? That's what I want to make sure. We have what are the symbols? 1, 2, 3, 4, 5, 6, 7. That's all, no? 1, 2, 3, 4, 5, 6, 7. Yes. So now these are disjoint. Is the LCM of 3 and 4. So that is 12. Just like that, here also we have to first express it as a product of disjoint cycles. 3, 4, 5, 2, 4, 5. 1 is not there anywhere, so we start with 2. 2 to 4, 4 to 5. So 2 to 5. 5 to 2, and that's it. So 5 to 2. Then let us take 3. 3 does not appear here. 3 goes to 4. 4 to 5, 5 to 3. So 4 to 3. Anything else? 2, 3, 4. Yeah, that's all we have. That's just it. So the order is LCM of 2 and 2, which is 2 itself. So that's just it. That is the solution. I have wiped that A is 3. Okay. Yeah. B is 12. Then C is 6. D is 6. E is 12 and F is 2. Yes. Then 6. What is the order of each of the following permutations? Two, 1, 5, 4, 6, 3. Two, 1, 5, 4, 6, 3. 2, 1, 5, 4, 6, 3. Okay. Then 1, 2, 3, 4, 5, 6, 7. 7, 6, 1, 2, 3, 4, 5. So that means here first we have to write them as products of disjoint cycles, and then we can find the order. So we straight away see the cycles. 1 goes to 2, 2 goes to 1. So that means this is a cycle. Then 3 to 5, 5 to 6, and 6 goes back to 3. And since 4 is unchanged, we don't write that here. And do you see that writing it also does not affect anything? If you write 4 here, that is a 1 cycle. So when you are calculating the LCM, you can take 1, that won't change anything. You can consider 1 or you cannot consider 1. So we choose to not write it. So the order of the permutation is LCM of 2 and 3, that is 6 P the given part. Oh, we have already written these things here, but there was no need to write this again anyway. So now this is our permutation. Let us start 1 to 7, 7 to 5, then 5 to 3, and then 3 again goes back to 1. So 2 is not appearing here. Let's start with 2, then 2 to 6, 6 to 4, 4 again goes back to 2. So is that it? We have 7 symbols, 4 and 3, 7, 1, 2, 3, 4, 5, 6, 7. Yes. Hence its order is the LCM of 4 and 3, which is 12. So that is the solution. 6 and 12. Yes. Next 7. What is the order of the product of a pair of disjoint cycles? Cycles of lengths 4 and 6. So here the cycles are not given, and it does not matter also. That is because ultimately what we need is the lengths of the disjoint cycles in order to calculate the order. The required order is This is important. Okay, disjoint. If we had only just 2 cycles, a 4 cycle and a 6 cycle, then their product does not necessarily have order 12. Disjointness is important. So that is just the solution to the 7th one. Then 8. Show that A8, the alternating group of degree 8, contains an element of order 15. So looking at how we are calculating orders of permutations, it is clear that we need two cycles, two disjoint cycles, one of which is a 3 cycle and the other is a 5 cycle. And so we can have, for example, this element. Consider element, or let us write permutation itself. In the symmetric group of degree 8. That means the group of permutations on 8 symbols. Now the question is this: is this also in the alternating group A8? That is this an even permutation? Even permutation, we know by definition, is a permutation that can be written as a product of 2 cycles where there are an even number of 2 cycles. For example, this permutation, the first one, the cycle itself, this is an even cycle because you can write it like this. What about this one? This is also going to be an even cycle. Eight, 7, 8, 6, 8, 5, 8, 4. Here there are 2 cycles, 1, 2. Here there are 4 2 cycles or transpositions. They are also called transpositions, 1, 2, 3, 4. So together, if we use these decompositions, this permutation is a product of 6 2 cycles, and that number 6 is even, so this is an even permutation. And from our study of permutation groups, we actually already know, we don't even have to consider these things. This is an odd cycle, that is, it is a 3 cycle, and 3 is odd. When that happens, then the cycle is an even permutation. This is also a 5 cycle, 5 is odd, so that is an even permutation, and product of 2 even permutations is again an even permutation. So that's why this is even. So we write like this. Since is a 3 cycle and this is a 5 cycle, both these belong to A8, hence their product is also in A8, and its order is of course what we want. Furthermore, the order of the product is 15. Is LCM of 3 and 5, that is equal to 15. If you want, you can take any other 3 cycle and another 5 cycle, only make sure that they are disjoint, that's all. Then 9. What are the possible orders for the elements of S6 and A6? What about A7? Okay. Now this is an odd numbered exercise, so its answer is available at the back of the text in the section called answers. I haven't seen that. So the solution I am now going to write, it may be a little naive, and there may be some clever, very short solution at the end of the text. Please check that out. Okay, so what we are now going to do, we are going to see the partitions of the number 6, that is the base in which we can write 6 as a sum of numbers, positive integers that are less than or equal to 6. For easy readability, I will write it in as a column 6, then 5 plus 1, then 4 plus 2, 4 plus 1 plus 1, 3 plus 3. In order to save space, let us use this space also. Although we normally don't write like that when we write a solution. If we are going like this, we maybe write the entire thing in the middle, and then after that we write whatever we want to write. Okay, so 3 plus 3, then 3 plus 2 plus 1, 3 plus 3 2's, then 2 2s and 2 1s, 1 2 and 4 1s, and lastly 6 1s. Why are we looking at partitions of 6? That is because these partitions correspond to cycle decompositions for any permutation in S6. Why that is the case, you will now see. There are 6 symbols, right? And our aim is to form disjoint cycles out of those 6 symbols. Let me just wipe this clean and then I am going to continue. Let us take a simple case. Suppose our set whose elements we are permuting has only 3 elements. Now the number 3 has these partitions: 1 plus 1 plus 1, 2 plus 1 and 3 itself. This corresponds to the cycle decomposition that looks like this. Each is a one cycle, that is and in particular this is the identity permutation. It does not change anything. Identity permutation where? In S3. This corresponds to a product of a 2 cycle and a 1 cycle. For example, and they are disjoint, keep that in mind. Or you can take other examples are also available. For example, 1, 3 and 2. We are concerned about the structure of the decomposition, not the permutations themselves. Okay, there are 2 more like this, and 3 corresponds to a single cycle of length 3. For example, this, and each such decomposition, this has a name. It's called the cycle structure of a permutation. For example, this permutation has the cycle structure 2, 1. That means it has a 2 cycle and a 1 cycle. This has the cycle structure 3. This has the cycle structure 1, 1, 1. And the way we are calculating orders of permutations, the order only depends on the cycle structure and not on the permutation itself. For example, if you want to calculate the order of this, say 1, 2, 3. Normally we don't write 3, but we are writing it here anyway. So what do we get? The order is 2. If in its place you had this, the order does not change because the order depends on the lengths of the cycles, not the cycles themselves. So that is why this will correspond to a particular type of order, this will correspond to another type of order, this will correspond to another type of order. So by looking at the partitions only, we can guess the order of those permutations whose cycle structures are like this. Okay, for example, this one, this corresponds to a product of 3 2 cycles, 3 transpositions. So that's why we are considering partitions. So let us now see the orders. I haven't I haven't entirely gone through this section from Gallian's book, so I'm not really sure how the author is denoting a cycle structure. We are just simply going to write like this. Each of these partitions corresponds to a cycle structure. Just we keep it till this cycle structure, and conversely if you have a cycle structure that also corresponds to a permutation. So there is a one-to-one correspondence between possible cycle structures and permutations of 6. Hence the possible orders are, we are just straight away going to write the things. This corresponds to a 6th cycle. There are many 6 cycles in S6, but we only want this number 6. All of them have order 6. So this is 6. This one is 5. LCM of 5 and 1. This one is, this time we are going to write it so that we don't directly write the orders, we show something in between how we are getting the order. So this is 4. This corresponds to, of course, 4, the order 4. This is LCM of 3 and 3, 3. Here LCM of 3 and 2 is 6, and this of course is 3. This is 2. Then this one is again 2. This one is directly 2. And the last one is a product of 6 1 cycles, and this cycle structure corresponds to a single element, that is the identity permutation, nothing else. So whose order is 1. Note that we are repeating numbers, so we are not writing it as a set, we are just writing it as a list. That is the possible orders are 1 is there, then 2 is there, this time we won't repeat, 3 is there, 4 is there, 5 is also there, and we have 6. And that's just it. You notice this thing. Although S6 is a very large group, and in fact it has 6 factorial number of permutations. How much is that? 6 times 5 factorial is 100, that means 720 elements are there in S6, but the order can be at most 6. it cannot go beyond that, it cannot go above that. Okay, so these are the possible orders that the elements can have in S6. Now what about A6? What about the alternating group? So from these partitions, we have to guess which cycle structures, or in other words, which of these partitions correspond to even permutations. The elements in A6 have cycle structures that correspond to the following partitions. From among these partitions, we have to now single out those that correspond to cycle structures of even permutations. So let us see which ones give us even permutations. There is something else also to be said about these partitions, but let us just finish this one. Okay. Is S6 cycle an even permutation? No. A cycle whose length is even is an odd permutation. So this will not appear. A 5 cycle is an even permutation because its length 5 is odd. Okay, it's just the opposite. So a 5 cycle is an even permutation, and this 1 cycle that is alongside it doesn't affect anything. So this corresponds to an even permutation. A 4 cycle is odd, but then combine that with a 2 cycle. A 2 cycle is also odd, so odd plus odd even. And we are saying odd plus odd because you considered this. You have a 4 cycle here, and along with that you have a 2 cycle here. We are saying that this is odd, so it can be written as a product of 2 cycles, an odd number of 2 cycles, and there is one extra 2 cycle. So that's why ultimately we get an even number of 2 cycles. So the permutation corresponding to this partition is an even permutation. So that means what we have to do here, consider the even numbers as odd, the odd numbers as even, and then you apply the rule for adding even and odd numbers. That is what you ultimately get. So this is odd, and there is nothing else to make that even, so this does not appear. Even plus even is even. Even plus odd is odd. No, this is even. Odd plus odd is 3 odds are there, so this will not give us an even permutation. Odd plus odd is even, so this will be there. This is odd, won't be there, and this one is even, of course, because each one is a 1 cycle, so each one is even, and together they also give us an even permutation. And in fact this is nothing but this corresponds to the identity element which is there in A6. We are considering 6 now, so that's why this will be there. So let us first write these partitions. Five plus 1. This time we can write normally 4 plus 2, 3 plus 3, 3 plus 3 ones, then 2 twos and 2 ones, and finally 6 ones. Hence, the possible orders of the elements of A6 are, since we have seen the thing once, I mean the LCMs, we can now directly write BC1 is there, so 1. LCM of 2 and 2 will give us 2. Here we have 3, so 3. LCM of 4 and 2 is 4, and we have 5 also. So these are all the possible orders. So you see that in A6 you will not find any element of order 6, because that is not a possible order. And something else is also asked now. Oh, what about A7? For A7 we need to consider the partitions of 7. For that we will not, however, write this elaborately. We will write it in a somewhat more compact form. Oh, okay. So here there are many more naturally. A7. Oh, I have not, have I written the partitions of 7? What are the, oh, so it's here, okay. So we are saying we would write compactly, and that's like this: 7, then 6 plus 1, then 5 plus 2, 5 plus 1 plus 1. Instead of writing 1 plus 1, we write like this: 2 times 1. Then 4 plus 3, then 4 plus 2 plus 1. If the numbers are different, we have to write them. Then 4 plus 3 ones, then 2 times 3 plus 1. So here, to distinguish these times from the numbers themselves, let us put the number of times something occurs within brackets, so that we don't get confused. So this means 3 plus 3 plus 1, then 3 plus 2 plus 2, then 3 plus 2 plus 1 plus 1, then 3 plus 4 ones, then 3 twos plus 1, then 2 2s and 3 1s. Then a single 2 and 5 1s, and finally 7 1s. So the possible orders, but it's not the entire S7, A7 we want. From among these we have to recognize the even ones. Okay, so let us now quickly recognize the even ones. The even ones are these 7. It's an odd permutation, and you can verify like how we verified there before this, which ones correspond to the even permutations. So then 5 plus 2 times 1, this one is even. Then 4 2 1, this one is even. Then 3 3 1, then 3 2 2, then 3 and 4 1s, that means this one. Okay, this one means this one along with that. Then 2 2s and 3 1s. And finally, of course, this is always there. So the order of this is 7, or let us write the final thing. The order of this is 1. Then here we have 2s and 1s. So the order is 2. Do we have a 3 order? Yes, 3 and 4 1s. So we have 3. And what about 4? We have 4 and 2 here. LCM of 4 and 2 and 1, if you want to consider that also, is 4. Then 5 and 2 1s give us 5. What else? 6. 3 and 2, 1 3 and 2 2s. So LCM of 3 and 2 and 2 is 6, and I think that's it. We should have a 7 also. Oh, 7 means this 7 cycle will have order 7. So these are the possible orders for the elements in the alternating group of degree 7. There is after this again a similar question. What is the maximum order of any element in A10, the alternating group of degree 10, for which we have to consider the partitions of 10. This I won't do in this video. See, that's why I am saying that if you go to the answers section, I am hoping that there is a much shorter way of calculating these things. Since I haven't seen that, I don't know. And I said that there is something else to say about the partitions. How do you find the partitions in the first place? That answer can be found in any good number theory book where you have a treatment of partitions, which is available in the literature. So we are not going to say anything on that because that is not actually group theory. So we are using partitions here. We are not studying partitions themselves. Ramanujan had many things to say about partitions. If you are interested in those parts, you can see Ramanujan's mathematics and what he said about partitions, the possible number of partitions and different types of partitions. Many things are there. Okay, so we are ending things here itself in this group exercises videos. After this, there is the Gallian rings also. So that's just it in this video. So see you in the next video.